Identify the name of the functional group in this formula. So our formula is CH3COCH3. It's very difficult to deduce which functional group it is by just looking at it. So let's draw the structural formula first, and we're going to be able to see which homologous series it is and ultimately which functional group it is. So we have a carbon that is bonded to 3 hydrogens, and after that we have a carbon that is bonded to another carbon and an oxygen. So we're expecting a double bond so that the carbon can have 4 bonds, and then the last carbon is bonded to 3 hydrogens. As you can see, we have a ketone, so is our answer C in 1.1? No, our answer is actually not C. The question is asking us to identify the name of the functional group. So even though this is a ketone, the answer is actually D, because the name of the functional group of ketones is carbonyl. So our answer is D for 1.1 and not C. 1.2. Which of the following is the empirical formula of 1.2-dichloroethane? In order to find the empirical formula, we need the molecular formula. So we have 1.2-dichloroethane. The structure will be something like this. So there we have our dichloro, and we have hydrogens elsewhere. This is 1.2-dichloroethane. We have 2 carbons, we have 4 hydrogens, and we have 2 chlorines. What we have to do now is to divide by the smallest number, and we're going to have our empirical formula. Our smallest number is 2, here and here. If we go ahead and do that, we're going to have CH2Cl. We divided every number by the smallest number. So which option is what we have here? That is option B. That is option B. So our answer to 1.2 is actually B. 1.3. Consider the structural formula of the organic compound below. Which of the following statements about the above compound is correct? So we're looking for the IUPAC name of the above compound, right? So instead of looking at our options, let's just name it ourselves, and then we'll just pick the option that corresponds with the name that we have. So first things first, the longest carbon chain. So I can have 1, 2, 3, 4, 5. And then I can also go down and have 1, 2, 3, 4, 5. That is 5. And then if I start here, I also have 1, 2, 3, 4, 5. If I go straight, I have 5 again. If I go up, I have 5 again. It doesn't matter where you go, you're going to end up with 5 carbons. So we can conclude and say that we have 5 carbons in our longest chain. Now what we need is the functional group. We have a double bond right here. So that tells us that this is an alkene. We have to start numbering our carbons from the side closest to the functional group. So from the left hand side. So we're going to have 1, 2, 3, 4, 5. On the second carbon, we have a methyl. And then on the fourth carbon, we have 1 methyl and another methyl. So our name will be 2,4,4- because we have 3 methyl pent-2-ene. This is our branches, and this is the number of carbons on our longest chain. This is where the functional group is, and this is how the name of an alkene ends. So which option is that in 1.3? It seems like it is option C, 2.4,4-trimethyl pent-2-ene. So our answer to 1.3 is C. Our answer to 1.3 is C. Let's move to 1.4. 1.4. From the following options, choose one that best explains why catalysts are so extensively used in chemical reactions. I think we use them so extensively because they speed up our reaction, they lower the activation energy. So option A says that catalysts can be used to drive the equilibrium in the desired direction. And then B says catalysts decrease the reverse reaction. We know that not to be true. And then C says catalysts have no effect on the reverse reactions. And then option D, catalysts can cause the forward and reverse reactions to proceed at a faster rate. We know that for sure, the lower the activation energy. So for 1.4, our answer is D. We use catalysts mainly because they cause the forward and reverse reaction to proceed at a faster rate. Let's look at 1.5. 1.5 says, study the following graph and match label X from the following choices. So let's look at label X. Before we even look at our choices, label X is our activated complex. And that seems like option B, activated complex. So the answer to 1.5 is B. So let's go to 1.6. 1.6, it says that the equation below represents a chemical reaction at equilibrium in a closed container. Which of the following changes will increase the yield of HI in the above reaction? So let's go ahead and do some analysis. HI is our product, right? If we're looking at the forward reaction, and then the forward reaction is exothermic. We can see that the enthalpy change is less than 0. Let's look at option A. They're saying that increase in temperature. Can we increase the yield of HI by increasing the temperature? Let's find out. Increasing the temperature favors endothermic reaction. And if we are saying that the forward is exo, the reverse is endo, right? So if you increase in temperature, HI is actually going to decrease because the reverse reaction is going to be favored. But looking at option B, decrease in the temperature. If you decrease the temperature, exothermic reaction is favored. So the forward reaction will be favored, and that will lead to more HI. So before even looking at option C and D, we can see that our answer is option B, right? Option C and D are actually not correct because they talk about pressure, and we have the same number of moles on the reaction side, on the reactant side, and then on the product side. So whatever you do to pressure, it's not really going to affect the yield. It will only affect the rate. And then moving to 1.7, which of the following solutions, each of concentration 0.1 moles per decimeter cube, has the highest pH? Right. So the highest pH, we're looking for the solution that is the most basic will have the highest pH. And then the first solution is HNO3. HNO3, we know fully well that that is an acid, so it cannot be our answer. And then option B, NH4Cl is an acid salt, so it will have a pH that is less than 7, so that cannot be our answer. On the other hand, Na2CO3 is a base, so maybe that can be our answer if we don't have another strong base. Option D is ethanoic acid. Obviously, that cannot be our answer. So for 1.7, the answer is actually C. That is the only basic solution that we have. Let's look at 1.8. 1.8 is saying a solution of ethanoic acid is titrated against a standard sodium hydroxide solution. Which one of the following indicators will be the most suitable for this titration? We have actually answered a very similar question. If you want to see the question I'm talking about, go to a playlist named Acids and Base. You're going to find the question right there. Ethanoic acid, it is a weak acid. So we have a weak acid plus sodium hydroxide, which is a strong base, So if you have a titration between a weak acid and a strong base, then the pH you will end up with will be greater than 7. Way greater than 7. We're going to use indicator A, which is phenolphthalein. If you had a strong acid and a weak base, we would use methyl orange. Right. Moving to 1.9. So in 1.9, which of the following correctly gives the direction as well as the medium in which electrons move in a galvanic cell? Without even looking at our option, the electrons move from the anode to the cathode. And then which medium, how do they move? They move through what? They move through an external wire. So that is option B. So the answer to 1.9 is B. They move from the anode to the cathode through an external wire, not through the salt bridge. No. And 1.10, which of the following F reactions occurs at the cathode during the electrolysis of a solution of concentrated NaCl? At the cathode, there's deposition. Something is deposited at the cathode. So we know that by just saying that option A cannot be our answer, and option C cannot be our answer. The only possible answers we have, which makes a bit of sense, is actually B and D. Can you please let me know in the comments which answer you're going with for 1.10? Homologous series to which compound B belongs to. So let's go to our compound B and see what is happening. It will be easy to see that compound B is an ester because of this functional group that we have here. Compound B is an ester. So the answer to 2.1.1, that compound B is an ester. And then the second question, 2.1.2, we're looking for the IUPAC name of the same compound. So this is how you actually name an ester, ladies and gentlemen. You're going to come here to the structure and you're going to put a line that divides the oxygen with the double bond from the oxygen with the single bond. And then the part of the structure that has the oxygen with the single bond is coming from the alcohol. And the part of the structure that has the oxygen with a double bond is coming from the acid, because we know that in order to form an ester, you need an alcohol and an acid in the presence of H2SO4. So let's look at our alcohol. Our alcohol that was used in making this ester is methanol. Why are we saying it is methanol? Because of this single carbon right here. And the acid that was used to make this ester is propanoic acid. Why are we saying so? These three carbons that we have there. So when we name this ester, the name is going to be methyl propanoid. Methyl propanoid. Right. So this methyl here is coming from the fact that the alcohol that was used is methanol. If the alcohol that was used was butanol, then the name would start by saying butyl. And then the propanoid is coming from the acid that was used, propanoic acid. Let's move to the second question, 2.2 and 2.2.1. An alcohol and an acid are heated in the presence of concentrated sulfuric acid to form compound B. Write down the role of the concentrated sulfuric acid in this reaction. So sulfuric acid in an esterification acts as a catalyst. So the answer to 2.2.1 is catalyst. It acts as a catalyst. It speeds up the reaction. You can also see that. And then the answer to 2.2.2, names of the alcohol and the organic acid used to prepare compound B. So we have already deduced which alcohol was used and which acid was used when we were naming our compound B, right? So now we're just gonna say the alcohol that was used is methanol and the acid that was used is propanoic acid. The acid that was used is propanoic acid. 2.2.3, name of the type of reaction that is taking place. Obviously the name of the reaction that is taking place is esterification. And other books will say condensation, which is also correct. I see that option time after time in memos. That is 2.2. Let's move to 2.3. So in 2.3, from the table above, consider compound C. So let's go to compound C and see what I have. Compound C, we have an acid. This is the functional group of an acid. Ethanoic acid to be specific. Let's go to the questions. 2.3.1. So the first question, 2.3.1, write down the name of the functional group of compound C. So we've already deduced that compound C is an acid, right? The name of the functional group of acids is carboxyl. So we have carboxyl group. That is the name of the functional group. And then 2.3.2, to which homologous group does compound C belong to? It is a carboxylic acid. That's an easy question to answer. It is a carboxylic acid. 2.3.3, differentiate between the terms functional group and homologous series. This question is actually just asking you to define homologous series and functional group. So let me just remind you, homologous series is a series of organic compounds that can be described by the same general formula. A series of organic compounds that can be described by the same general formula. While functional group, on the other hand, is a bond or an atom or a group of atoms that determines the physical and chemical properties of a group of organic compounds. There we go. You just need to define functional group and homologous series for 2.3.3. 2.4, for the table above, from the table above, actually, consider compounds A, D, and F. And then the first question, write down the homologous series to which they belong to. So let's go to compound A. Compound A, we have an OH, which is the functional group of an alcohol. So we know that compound A is an alcohol. And then compound D, we also have another OH, so that is another alcohol. Let's look at compound F. It ends with ol, so we have another alcohol again. So A, D, and F are alcohols as far as the homologous series is concerned. So the answer to 2.4.1 will be alcohols, because A, D, and F are all alcohols. 2.4.2, compound A and D are isomers. As what type of isomer will they be classified? So let's go to A and D. A and D. So A, let me just write down A real quick for the sake of clarity. So for A, we have something like this. We have hydrogens everywhere else. And then let's look at D. So for D, we have condensed structural formula, which we're going to write in full now. So we have a carbon with 3 hydrogens. We have the second carbon, and then on the second carbon, we have 1 hydrogen and an OH. And then the third carbon with 3 hydrogens. So what type of isomers is compound A and D, not B? Excuse me, compound A and D. So compound A, the OH is on the first carbon, and then for compound D, the OH is on the second carbon. So they have the same molecular formula, but just different position of the functional group. So those are called positional isomers. So 2.4.2, the answer here is positional isomers. They will be known or referred to as positional isomers, compound A and D. The third question, 2.4.3, we asked to draw the structure of compound F. Let's go ahead and look at compound F. So for compound F, 2-methyl-propane-2-ol. So let's start with the prop. So as soon as we see prop, we know that we need 3 carbons. So we have 1, 2, 3, and then 2-ol. This 2-ol tells us that the OH is on the second carbon. So let's have that OH right here. And then this 2-methyl, we have a branch on the second carbon. So we're going to have 1 carbon there. And then now we just left out with the hydrogens. And we have the structural formula of compound F just like that. Let's go ahead and move to 2.5. So 2.5, we're interested in compound G and compound E. 2.5.1, we're supposed to name compound G. Let's go to compound G. So compound G, the first thing that we must look for is the longest carbon chain. It is easy to see that this will indeed be our longest carbon chain. Let's count that. 1, 2, 3, 4, 5, 6. That is hex. And then as soon as I see Br, I know that it is a haloalkane, right? So it will be hexane. Now I'm just left with the branches. Where do I start numbering? If you start numbering from the left, on the second carbon, you have Br, you have bromo. And then if you start numbering from the right, on the second carbon, you have methyl, you have dimethyl, right? So the question now is, what takes preference between a branch and a halogen? Well, according to the exam guideline, nothing takes preference between the halogen and the branch. You just have to start numbering from the side that will lead to the smallest number. What do I mean by that? If we start numbering from the left, then we're going to have 2 for brom, right? And then this is 2, 3, 4, 5. And then we're going to have 5,5 for that dimethyl. And then these numbers will give us 12. If we start numbering from the right, we're going to have 2.82 for the dimethyl, right? And then we're going to have 5 for the bromo. So this is 2 plus 5, which is equals to 9. If we start numbering from the right, we have the smallest number, and that's what we need to do. Nothing is going to take preference between the halogen and the branch. So we're going to have 5 bromo. Dash 2.2 dash dimethyl hexane. 2.2 dash dimethyl hexane. And that is the name of our compound G. The last question, structural formula of compound E. Let's go ahead and look at compound E. So compound E, we have 2.4 dimethyl pent 1-ene. So pent, 5 carbons, 1, 2, 3, 4, 5. And then we have a double bond on the first carbon. We can tell from this pent 1-ene. So there we go. We have a double bond. And then on the second carbon, we have a branch with 1 carbon. And then on the fourth carbon, we also have another branch with 1 carbon. So now we're essentially done. We just left with filling out the hydrogens. So let's go ahead and do that. Yeah. So 1, 2, 3. We still need another hydrogen. And then 1, 2, 3. It's a painful exercise, but yeah, we have to do what we have to do. Compound A and B are functional isomers, like we are told in 3.1.1. What we are actually required to do is define the term functional isomer. Like all isomers, we have the same molecular formula, but in this case, the compounds differ by functional group. So the definition for functional isomer, same molecular formula, but different functional groups. Let's look at 3.1.2. Write down the IUPAC name of compound B. So the first thing you want to do is to determine which homologous series this compound B belongs to. Because of the structure of the functional group, compound B, it's a ketone. This carbon that is bonded to the oxygen is bonded to 2 other carbons. And because of that, we can conclude and say that compound B is a ketone. Now what we need is the longest carbon chain. Clearly, it is easy to see that this will be our longest carbon chain with 1, 2, 3, 4, 5 with 5 carbons. So we know we have pentane. Now what we need, or what we're looking for, is the position of the carbon that is bonded to the oxygen. If we start numbering from the left, we're going to have 1, 2, 3. If we start numbering from the right, we're going to have 1, 2, 3. So where we start numbering really doesn't matter. Our functional group is on the third carbon. So we're going to have pentane 3-one. That is the answer to 3.1.2. Let's look at 3.1.2. 1.3. How does the boiling point of A compare to that of pentane 1-ol? So we have pentane 1-ol and compound A. Write down only greater than, equal to, or lower than. So let's go to compound A. Compound A is an aldehyde because the carbon that is bonded to the oxygen is only bonded to one other carbon. So that makes it an aldehyde. So we have pentane 1-ol and pentanol. Pentane 1-ol is an alcohol. So it consists of hydrogen bonding. We have hydrogen bonding in alcohols. And then pentanol is an aldehyde. It consists of dipole-dipole. So the intermolecular forces in pentanol is dipole-dipole. So in order to answer this question, you actually need to know which intermolecular force is generally stronger between hydrogen bonding and dipole-dipole. Compound A will have a lower than boiling point compared to pentane 1-ol. Let me explain why that is the case in 3.1.4. The intermolecular forces in pentane 1-ol, which happens to be hydrogen bonding, are stronger than the intermolecular forces in pentanol, which is dipole-dipole. And then you know that if you have stronger intermolecular forces, then more energy is required to overcome those intermolecular forces in that compound. And then as a consequence, the alcohol or pent 1-ol will have a higher boiling point. That is the answer to 3.1.4. Let's look at 3.1.5. How will the vapor pressure of compound B compare to that of pentane 1-ol? Right, only higher than, lower than, or equal to. Explain the answer fully. So compound B, like we've already deduced, is a ketone. And which intermolecular forces do we find in ketones? We have dipole forces. And then again in pentane 1-ol we have hydrogen bonding. In pentane 1-ol we have hydrogen bonding. So that will lead to ketone having a higher than vapor pressure compared to pentane 1-ol. Higher than vapor pressure. So what you have to understand is that the weaker the intermolecular forces, then the higher the vapor pressure. So between compound B, our ketone, and pentane 1-ol, pentane 1-ol has stronger intermolecular forces. So it will require more energy to overcome the intermolecular forces. And then as a consequence, it is going to have a lower vapor pressure. It is going to have a lower vapor pressure compared to ketone. Ketone will actually have a higher vapor pressure. So what you need to memorize, or what you need to know, is that the stronger the intermolecular forces, the higher the boiling point, the higher the melting point, but the lower the vapor pressure. You need to know that. 3.2.1. Let's define the term boiling point. That is not the temperature at which liquid turns to gas. Please, we no longer use that definition at this level. It is actually the temperature at which the vapor pressure equals the atmospheric pressure. The temperature at which the vapor pressure equals the atmospheric pressure. That is boiling point. 3.2.2. Run down the independent variable for this investigation. Let's take a look at what is happening in this question. Let us use compound C to E to investigate one factor which influences the boiling points of organic compounds. What I'm realizing real quick is that in compound C we have 1, 2, 3, 4. We have 4 carbons, right? And then in compound D, we have 1, 2, 3, 4, 5. We have 5 carbons in compound D. And then in compound E, we have 1, 2, 3, 4, 5, 6. We have 6 carbons in compound E. So it seems like our independent variable here, what we are changing is actually the chain length. We can see that from the number of carbons we have in the compounds. So the answer to 3.2.2 would be chain length, or the molecular mass, because as the chain length increases, then the molecular mass is also going to increase. So that is the independent variable. And 3.2.3, write down the type of van der Waals force that occurs between these organic compounds. So these organic compounds are all alkenes, right? Well, you can draw compound C fairly quick by saying C 1, 2, 3 hydrogens, and then another carbon with 2 hydrogens, another carbon with 2 hydrogens, and the last carbon with 3 hydrogens. The same thing with compound D and E, they're all alkenes. So the force that is occurring in compound C, D, and E is actually London force. That is London force, or induced dipole forces. Well, let's look at 3.2.4. Write down the conclusion that can be drawn about the boiling point of straight chain alkenes. So let's look at our diagram. We can see fully well that as the number of carbon is increasing, our boiling point is increasing from -1 to 36.1 and lastly to 69. So we can conclude and say that as the chain length increases, the boiling point increases. If you had said molecular mass in 3.2.2, you would say that as the molecular mass increases, the boiling point increases. How can we boil down these complex concepts to a few bullet points? Well, if a reaction starts with an alkene and you get whatever product you're going to get, then that reaction is an addition reaction. If a reaction starts with whatsoever it is starting with and it ends up with an alkene, then that reaction is an elimination reaction. And if our first condition is not met and our second condition is not met, then that reaction is a substitution reaction. What am I even saying? Let me show you what I'm talking about by answering this question. Let's look at 4.1. Consider reaction A and write down the type of reaction that takes place. So reaction A is right here. So let me go through my conditions and see which one is met. Do we start with an alkene? No, we don't. We start with a secondary alcohol. Do we end up with an alkene? Yes, we do. We have propene as our product, right? So we know fully well that from that only, our reaction is an elimination reaction. Our second condition is met. So the answer to 4.1 is elimination. It's elimination. Just because we know that if a reaction ends with an alkene, it's elimination. If it starts with alkene, it's addition. And then if none of that is correct, then it is a substitution reaction. Let's do 4.2 and 4.2.1. Reaction B represents a hydration reaction. Let's look at B. At B, we're starting with propene and we end up with a secondary alcohol. And then we are told that that reaction is a hydration reaction. Right. And then now what we are asked to do is to define hydration reaction. It is the addition of water to a compound. That's it. That's the definition. It's the addition of water to a compound. That's what we mean when we talk about a hydration reaction. We add in H2O to a compound. And the follow-up question, 4.2.2, write down the name or formula of the catalyst used for this reaction. So a catalyst you can use for a hydration reaction is H2SO4. So we can use sulfuric acid as a catalyst for a hydration reaction. Let's look at 4.3 and 4.3.1. During reaction C, a specific rule is followed to determine the major product when HBr is added. Let's look at reaction C. So for reaction C, we are starting with propene and we end up with 2-bromopropene. So let's go back to our conditions. Do we start with an alkene? Yes, we do. So we know that reaction C is supposed to be an addition reaction. Well, the answer to 4.3.1 was actually very difficult to find. But if you visit the KEBS document and other relevant resources, you'll find out that for hydrohalogenation, our addition reaction in this case, we need no water because alkenes cannot react with pure water. And then apart from needing no water, we need a concentrated strong acid. So we need a concentrated strong acid for this reaction that we have in 4.3.1. It is an addition reaction, namely hydrohalogenation. we're adding a hydrogen and a halogen. 4.3.2, use structural formula and write down the balance equation for this reaction. So propene plus HBr. Let's go ahead and do that. So we're going to have 1, 2, 3 carbons, right? So 1, 2. Now we just need to add our hydrogens, and we're supposed to have something like that, plus HBr to give us something. If you look back to the equation statement, it says that during reaction C, a specific rule is followed to determine the major product when HBr is added. So now you actually have to know that rule in order to answer this question. Well, to some extent, we know that this double bond is going to break, and either one between H and Br is going to come to the second carbon, and then the other is going to come to the first carbon. So do we get Br on the second carbon, or do we get Br on the first carbon? You need to know where to place that Br, because if you place it at the wrong location, then you lose a mark. But there's a rule for that. There's a law for that. Markovnikov's rule. So basically what it is saying is that the hydrogen is going to go where there's a lot of hydrogens, and then the halogen is going to go to the other spot. So if you look at this carbon here, it has 2 hydrogens, and then the carbon in the middle has 1 hydrogen. So the hydrogen will tend to go to the carbon with a lot of hydrogens already. So that Br, it will usually go to the middle, because that's where we have the least number of hydrogen. So our product is going to look like this. Br is going to come to the carbon in the middle, and the hydrogen is going to come to the first carbon. And then now it's just a matter of filling out our hydrogens. So this is our major product according to Markovnikov's rule. And then Br being on the first carbon and H being on the second carbon is our minor product. This is our major product. Yeah, usually when this reaction occurs, this is the product, right? 4.1. Identify the type of reaction taking place at, so let's go to reaction D. Reaction D. Yeah, this one is going to be easy because we know our conditions. Do we start with an alkene? No. Do we end with an alkene? No. So we know that it is substitution. It is substitution. There isn't a lot to think about there. And then 4.2. Which reaction are we interested in? We are interested in reaction F. In reaction F, do we start with an alkene? The answer is no. Do we end with an alkene? The answer is still no. So again, that is a substitution reaction. That is a substitution reaction. It cannot be otherwise. And then 4.5.1. Reaction E is a hydrogenation reaction. Let's look at reaction E real quick. We're starting with propene and we're ending up with propane. So it is indeed a hydrogenation, right? And then what does the equation say? Write down the 2 reaction conditions for this reaction. 2 reaction conditions for hydrogenation. So we need heat, and another thing we need is a catalyst. We need a catalyst. Yeah, which catalyst in this case? We need palladium, platinum, nickel, and so on. Right. And then 4.5.2. Name one use of hydrogenation in the food industry. Well, I will leave that one to you. It is actually easy to see that the forward reaction is endothermic. The energy of the products is greater than the energy of the reactants. So the answer to 5.1.1, our reaction is endothermic. 5.1.2, calculate the heat of reaction for the forward reaction. So what is the heat of reaction, or the enthalpy change? Is the energy of the products minus the energy of the reactants. Let's look at the energy of the products first. our products have an energy of 420 kilojoules per mole, while the reactants start with an energy of 0 kilojoules per mole. So our enthalpy change will be 420 minus 0, which is just equals to 420 kilojoules per mole. That is the answer to 5.1.2. Looking at 5.1.3, write down the activation energy for the reverse reaction. Now we are interested in the activation energy for the reverse reaction. So the activation energy for the reverse reaction will be this energy here at peak, which is 480 kilojoules per mole, minus the potential energy of our reactants. For the reverse reaction, that will be 420 kilojoules per mole. So we have the activation energy being equals to 480 minus 420, which is equals to 60 kilojoules per mole. Right, that is the answer to 5.1.3. Let's look at 5.2. The following graph represents the number of particles against a specific amount of kinetic energy of the molecules. The data for samples R and S was obtained at different temperatures, which affects the rate of reaction. There we have a graph for R and S. We have the number of particles on the y-axis and the kinetic energy of the particles on the x-axis. The first question, 5.2.1, is asking us to define the term rate of reaction. That is the change in concentration of the reactants or product per unit time. It is actually that easy. 5.2.2. What does the area to the right of line T represent? Let's go to our graph and see what we have. We have a line T there. So what does this area to the right of line T represent? You should know by now that that area there represents the number of particles. So that is the number of particles with a kinetic energy that is equals to or greater than the activation energy. The number of particles with sufficient energy. That is 5.2.2. Moving to 5.2.3. Which sample was at a higher temperature? Write down only sample R or sample S. So we know that when temperature is increased, more particles will have sufficient kinetic energy. So the graph that has a lot of particles with sufficient kinetic energy was obtained when the temperature was increased. If you look at R, the number of particles with sufficient kinetic energy is given by this graph here. But if you look at S instead, you will realize that not only is it given by that graph for R, but even this portion right here. So we can conclude from that and say that the answer to 5.2.3 is actually sample S. Another way of seeing it is that when temperature is increased, the peak is gonna go down and it is gonna shift to the right, just like what happens with S. Let's move to 5.2.4. 5.2.4. Explain the answer to question 5.2.3 by using the collision theory. So we know fully well that when the temperatures increase, the particles will gain kinetic energy. The average kinetic energy of the particles is going to increase. And then more particles will have sufficient kinetic energy. That is the kinetic energy that is equals to or greater than the activation energy. So the area under the graph to the right of line T should increase, just like we saw with sample S. 5.3. In 5.3, the question is saying that 11 grams of magnesium ribbon reacts with a 0.25 moles per decimeter cube of hydrochloric acid solution at a temperature of 25 degrees Celsius according to the following balanced reaction. There we have it. A table of the results is given below. The first question, use the graph paper that is printed on the last page of the question paper and plot a graph for this result. So even though we don't have graph paper. Let's see what we can do here. So we have our y-axis and we have our x-axis. On our x-axis, we're gonna have the time, obviously. So let's have an interval of 1. So we're gonna have 1, 2, 3. And then on the x-axis, that is time in seconds. And then on the y-axis, we have the volume. We have the volume in centimeter cube, right? And then we have 0 to 35. So let's move with an interval of 10. So let's say 1, 2, 3, 4. Those 4 blocks will give us 10. So we have 10, and then 1, 2, 3, 4. Let's have 20. 1, 2, 3, 4. Let's have 30. And then 1, 2. Let's say that is 35. Right. So our first coordinate, we have 0 and 0. So let's just put a bullet point here. And then we have 0.5 and 17. So 0.5 and 17 somewhere here. We have another bullet point right there. 1 and 25. So we have 1 and 25 somewhere here. 1.5 and 30. So midway between 1 and 2 and 30. So something like that. And then 33 and 2. So 33 and 2. 35 and 2.5. 35 and 2.5. And again, 3 and 35. We should have something like that. 5.30.2. Use the graph paper and explain what happened with the reaction between 2 minutes and 3 minutes. So let's go ahead and look at that. We're interested in 2 and 3. We are interested in 2 and 3. So let's see what happens at that point. You can see clearly that our line flattens out. Our gradient goes to 0. Our reaction is completed. It is no longer taking place. So that's what happens between t is equals to 2 and t is equals to 3 minutes. Actually, here on the x-axis, it's actually not seconds, but minutes, right? 5.3.3. So in 5.3.3, the question is saying, in a second experiment, the concentration of the hydrochloric acid changed from 0.5 to 1 mole per decimeter cube. Draw a new curve on the same graph paper to show what effect it will have. Label the new curve X. So the concentration of hydrochloric acid has now increased from 0.25 to 1 mole per decimeter cube. So we would expect the rate of reaction to increase. The graph, the new graph that we are supposed to catch, should have a steeper gradient versus the graph we have already, right? So we expecting something like this. It should have a steeper gradient and it should reach completion before our initial graph. So that's what we're supposed to have. If your graph is below your initial graph, then that is totally wrong. You are saying that the rate of reaction is now decreased, which is not the case. Right, the last question, 5.3.4. Assume that the molar gas volume at 25 degrees Celsius is 24.47 decimeter cube per mole. Calculate the volume of acid that was used in the first experiment when the reaction was completed. So in the first experiment, we have a volume at the end of our reaction, which is 35 centimeter cube of H2, right? So let me just copy again. Let me just copy down that equation again. So we have Mg plus what? Plus 2HCl. And we get MgCl2 plus H2. At the end of our reaction, we have some volume of H2, which is 35 centimeter cube. And we are also given the molar gas volume. So we can use that information to find the number of moles of H2. And then from the number of moles of H2, we can find the number of moles of HCl using the balancing coefficient. The concentration initially is given to us as 0.2 moles per decimeter cube. So it should be easy to actually find the volume like we are asked to do. Let's go ahead and do that. So for H2, we're saying that the number of moles is equals to the volume divided by the molar gas volume. So that will be equals to, so the SI unit for our molar gas volume is in decimeter cube. So we have to convert the volume of H2 to decimeter cube. That will give us 35 divided by 1,000, and then everything divided by 24.47. Now it is just a matter of putting that in your calculator to get 1.43 times 10 to the minus 3 moles. Right. So now balancing coefficient, the number of moles of H2 divided by the number of moles of HCl is equals to 1 divided by 2. So the number of moles of HCl will be equals to the number of moles of H2 multiplied by 2. And if we do that, we're going to get 2.86 times 10 to the minus 3 moles as the number of moles of HCl. And the last step, concentration, is number of moles divided by the volume. So the volume will be equals to the number of moles divided by the concentration. The number of moles is 2.86 times 10 to the minus 3. The concentration is 0.25. That is 0.011 decimeter cube. As you can see, we want to calculate Kc, the equilibrium constant. We have a reaction between nitrogen gas, hydrogen gas to give us ammonium. The actual question reads as follows. 5 moles of nitrogen gas and 5 moles of hydrogen gas are sold in a 5 decimeter cube empty container. Equilibrium is reached at 450 degrees Celsius. Upon analysis of the equilibrium mixture, it is found that the mass of ammonia is 20.4 grams. Calculate the value of equilibrium constant at 450 degrees Celsius. We can see fairly quick that the initial number of moles of nitrogen gas is 5 moles. So we're going to go ahead and put that here. And then the initial number of moles of hydrogen gas is also 5 moles. So we're going to put that here. They are sealed in an empty 5 decimeter cube container. So the initial number of moles of ammonia is actually 0 moles. From there on, we are told that the mass of ammonia at equilibrium is 20.4 grams. So here at equilibrium, we have 20.4 grams. But the problem with that is that we actually need the number of moles and not the mass. So we have to convert that mass to number of moles by saying that the number of moles will be equals to the mass divided by the molar mass. So that is going to be 20.4 divided by the molar mass of nitrogen, that is 14. And then the molar mass of 3 hydrogen, that will be plus 3. If you put that in your calculator, you should get 1.2. Now we can say that the number of moles of NH3 at equilibrium is 1.2. What will be the number of moles of H2 at equilibrium? What will be the number of moles of N2 at equilibrium? If we use the balancing coefficients, we can say that the number of moles of nitrogen gas will decrease by minus X, while the number of moles of hydrogen gas will decrease by minus 3X. But then ammonia, at the other hand, the number of moles are increasing, so they are increasing by plus 2x. Where am I getting the minus 3x and the plus 2x? I'm getting it from the balancing coefficients. The balancing coefficient of hydrogen gas is 3 and the balancing coefficient of ammonia is 2. The number of moles of nitrogen gas at equilibrium will then be equals to 5 minus x, while the number of moles of hydrogen gas at equilibrium will be 5 minus 3x. On the other hand, the number of moles of ammonia at equilibrium will be 0 plus 2x. But we have already deduced that that will be equals to 1.2. We know that this will be equals to 1.2. If 0 plus 2x is equals to 1.2, then what is the value of x? The value of x will clearly be 1.2 divided by 2, which is just 0.6. So here we have plus 1.2. Here we're going to have minus 1.8, and here we have minus 0.6. That is because we know now that x is actually equals to 0.6. So the number of moles at equilibrium of nitrogen gas, 5 minus x, that will be 4.4 if x is equals to 0.6. On the other hand, 5 minus 3x, that will give us 3.2. And for ammonia, we already know that we have 1.2 at equilibrium. Now we need the concentration at equilibrium. How can we find the concentration at equilibrium? We already have the numbers of moles. So in order to find the concentration, we just have to divide that by the volume. The volume is given to us as 5 decimeter cube. So we're going to use that. 4.4 divided by 5, that will give us 0.88. 3.2 divided by 5, it will be 0.64. 1.2 divided by 5, that is 0.24. So now we can say that Kc is equals to the products divided by the reactants. So based on our equation, we're going to have NH3, the concentration of NH3 at equilibrium, to the power 2 because of the balancing coefficient, divided by the concentration of N2, the concentration of N2, multiplied by the concentration of H2 to the power 3, again because of the balancing coefficient. So this will all be equals to the concentration of NH3 at equilibrium, that is 0.24. We square that and then divided by the concentration of N2 at equilibrium, 0.88, multiplied by the concentration of H2 at equilibrium, which is 0.64 to the power 3. If you put that in your calculator, you should get a Kc value of 0.25. If a substance produces hydrogen ions or hydronium ions, according to the Arrhenius theory, it is an acid. That is the answer to 7.1. Let's look at 7.2 and 7.2.1. Consider the following acid-base reactions. We have reaction X and reaction Y. The first question is saying, from reactions X and Y, identify the reaction that illustrates the Arrhenius theory. So just to recap, just to go over it again, an acid is a substance that produces H plus or H3O plus. So now we're going to go to reaction X and reaction Y and see if we have a substance that is producing H plus or H3O plus. If we go to reaction X, you will see fairly quick that HF is producing H3O plus. It donates a hydrogen. While on the other hand, we cannot say the same about reaction Y. There is no H plus produced or H3O plus. So our answer to 7.2.1 is X. Y, on the other hand, it is a good example of the Lowry-Bronsted theory. Let's look at 7.2.2. Write down a balance equation for the hydrolysis of NH4 plus ions. So we have NH4 plus H2O. Well, is NH4 plus an acid or a base? I know that it is an acid, but what if you were not aware of that? Let's look at reaction Y again. If you look at the reverse reaction, we have NH4 plus NO3 minus. And what does NH4 plus do? It donates a proton to become NH3. So clearly it is an acid because it is donating a proton. You should be able to conclude that NH4 plus is an acid even if you didn't previously know. So in this reaction, if it donates a proton, we're going to have NH3 plus H3O plus. There we go. That is our answer to 7.2.2. On the other hand, 7.2.3, will the resultant solution from question 7.2.2 be acidic, basic, or neutral? Give a reason for your answer. It is going to be acidic. Why are we saying it is going to be acidic? That is because H3O plus is produced. Right. If OH minus was produced, then it was going to be basic. But then in this case, we have H3O plus. Let's move to 7.3. So in 7.3, a sodium hydroxide solution is prepared by dissolving 4 grams of sodium hydroxide in water to make a 500 centimeter cube solution. The first question, 7.3.1. Calculate the concentration of the sodium hydroxide solution. We have the mass 4 grams. We have the volume 500 centimeter cube. How can we find the concentration? We can say that the concentration is equal to the mass divided by the molar mass multiplied by the volume. Right. This is the same as saying that the number of moles is equal to the mass divided by the molar mass, and then saying that the concentration is equal to the number of moles divided by the volume. This formula here just combines these 2 steps into one. Well, studies. Let's go ahead and substitute. The mass is 4 grams. The molar mass of NaOH, sodium hydroxide, it is actually 40, and then the volume is 500 centimeter cube. But we know fully well that we cannot use 500 centimeter cube. We have to convert it to decimeter cube by dividing by 1000. 500 divided by 1000, that is 0.5. And if you put that in your calculator, you shall get 0.2 moles per decimeter cube. So that is our concentration of sodium hydroxide. 7.3.2. During the titration, 12.5 centimeter cube of sodium hydroxide solution neutralizes 25 centimeter cube of a sulfuric acid solution according to the following balanced equation. Right, we have our equation right there. Sodium hydroxide plus sulfuric acid reacting to give us Na2SO4 plus H2O. What we are required to do is to calculate the pH of the H2SO4 solution. We know that pH is equal to minus log of H plus or H3O plus. If we find the concentration of H2SO4, we can find the concentration of H plus and consequently calculate our pH. We have a neutralization reaction. So we can say that the concentration of the acid multiplied by the volume of the acid divided by the concentration of the base multiplied by the volume of the base is equals to the number of moles of the acid divided by the number of moles of the base. Because these 2 substances are neutralizing each other, the number of moles of acid divided by the number of moles of base will be equal to just the ratio of the balancing coefficient if they indeed neutralize each other. So we can only set up this equation if they neutralize each other. If they don't neutralize each other, you actually cannot use this equation. Right, let's go ahead and substitute. The concentration of the acid, we are looking for that, the concentration of the acid. The volume of the acid that is used, we're told that the sodium hydroxide neutralizes 25 centimeter cube. So we have 25 divided by the concentration of the base. We calculated it in 7.3.1 and we found that it is 0.2 multiplied by the volume of the base, which is 12.5 centimeter cube. That is the volume that was used. We have 12.5 being equals to the number of moles of acid divided by the number of moles of base. Like I've said, we can use the balancing coefficient because they neutralize each other. The balancing coefficient of the acid is 2, while the balancing coefficient of the base is 2, while the balancing coefficient of the acid is 1. So we're gonna have 1 divided by 2. So now we just need to find the concentration of the acid. Let's do a bit of math. If we cross multiply, we're going to get concentration of acid multiplied by 25 multiplied by 2 being equals to 1 multiplied by 0.2 multiplied by 12.5. If we divide both sides by the coefficient of the acid, so we divide it by 25 multiplied by 2. And we also divide on the right hand side by 25 multiplied by 2. So the concentration of the acid is going to be equals to 0.05 moles per decimeter cube. Right, so now we have the concentration of the acid, but let me just remind you, we're not looking for the concentration of the acid per se, but the concentration of H plus or H3 or plus. You have to realize that H2SO4 gives you 2H plus SO4 2 minus. This is to say that if the concentration of H2SO4 is 0.05, then the concentration of H plus should be 0.05 multiplied by 2, which is just 0.1. So that's actually the concentration we're supposed to use to calculate our pH. The pH is equals to minus log of H plus, which happens to be 0.1. And if you put that in your calculator, you're going to have pH being equals to 1. 3 conditions for a galvanic cell to operate. Well, why are we saying it's a galvanic cell? We have half cell A and half cell B. We have 2 half cells. As soon as we see 2 half cells, we know that it is a galvanic cell. If we had only one solution, then it will be an electrolytic cell. Back to the conditions. The first condition, we need a temperature of 25 degrees Celsius. The second condition, we need a concentration of 1 mole per decimeter cube. And if you have gases, you're going to need a pressure of 1.03 times 10 to the power 5. Let's look at 8.2. Which half cell between A and B is the cathode? Look at this electron traveling from half cell A to half cell B. For a galvanic cell, the electrons move from the anode to the cathode in the external circuit. Where the electron is coming from is our anode, and then where the electron is going to is our cathode. So 8.2, the answer is actually B. B is our cathode. And the following question, 8.3, write down the half reaction that takes place in half cell A. We need to determine whether we're going to have barium or copper at the anode. At the anode, that's where we find our reducing agent. Between barium and copper, barium has a higher reducing ability. So it is barium that is losing electrons at the anode. In the following way, we have Ba losing 2 electrons to give us Ba2 plus 2 electrons. This is the half reaction that is taking place in half cell A. 8.4, we need to write down the cell notation for this cell. Generally, it looks like the following. We have the anode, we have our bridge, and then we have the cathode. At the anode, like we've already deduced, we have Ba that loses 2 electrons to form Ba2 plus. And then at the cathode, we have copper 2 plus that is going to gain 2 electrons to become copper. That's all we need to do for 8.4. 8.5, on the other hand, we want to calculate the EMF of the cell. So the EMF of the cell is equals to the potential difference at the cathode minus the potential difference at the anode. At the cathode, we have copper, and the potential difference is 0.34. Minus the potential difference at the anode, we have barium, of which that is minus 2.9, to give us an EMF of 3.24 volts. How will an increase in the temperature of the solution affect the EMF? Will it increase, decrease, or remain the same? The voltage and the temperature are inversely proportional to each other. So if there is an increase in the temperature, the EMF of the cell will actually decrease. So the answer here is decreases.